Hello, students. I am Mohammed Ali. Welcome to my virtual classroom. And let's begin with today's lecture. Enjoy. Hello, everyone. This is Chemical Energetics, and it's episode 2. And now we learn about enthalpy of hydration and enthalpy of solution. And I really expect that in episode 1, you would have learned lattice energy to your best. So here we go. Firstly, with enthalpy of hydration. Okay. So basically, enthalpy of hydration, remember, it's of an ion. Like for lattice energy, it was of a compound, but hydration is of ion, and it's always exothermic, right? So basically, if I have a gaseous ion, and if I actually dissolve it in water, so the energy released is simply called as enthalpy of hydration. So what is enthalpy of hydration? So it is the enthalpy change when 1 mole gaseous ion is dissolved in water to give infinite dilute solution. Okay, the word actually dissolved, it carries immense importance. Immense importance. It is a physical process. The ion needs to get dissolved. I mean, it should not react. So basically, which ion actually react with water? It's a high charge density ion, right? Now, please, on a side corner, please remember that high charge density ions react with water. For example, oxide ion. Oxide ion does not have enthalpy of hydration. If you add oxide ion in water, so I think that oxide ion converts into hydroxide ion. Now, this is not a physical process. I mean, it is not enthalpy of hydration even. So, like in the examination, some students actually feel that how would we come to know that which ions are high charge density ions? So guys, it's what we'll tell you. We'll simply ask you that this ion does not have enthalpy of hydration. Why? So just tell us that because it's high charge density ion and it will react with water. By the way, this reaction is actually hydrolysis, right? So we'll be talking about low charge density ions, or we'll actually limit ourselves to a certain charge density which does not exceed a certain value, which may react with water. Now, if I come back to the original point, and for example, if I have sodium ion in the gaseous state, if I add in water, it forms sodium ions aqueous. It's called as enthalpy of hydration of sodium ion. For example, if I have chloride ion gas, if I add in water, it forms chloride ion aqueous. It's called as enthalpy of hydration of chloride ion. And what if I add them together? Let's say if I have Na plus gas, chloride ion gas, it gives you Na plus aqueous plus chloride ion aqueous. So if I ask you, what is this value, enthalpy of reaction? So I think it will be equal to enthalpy of hydration of sodium ion plus hydration of chloride ion. Or let's say, for example, if I have calcium ions gas plus, let's say, 2 bromide ion gas, now it gives you calcium ions aqueous plus 2 bromide ion aqueous. Remember, enthalpy is of 1 mole. So now in this case, the enthalpy of reaction should be equal to enthalpy of hydration of calcium ion plus 2 into enthalpy of hydration of bromide ion. Now in this case, some students actually forget these moles. They forget these moles. Please do not forget these moles because it's a common mistake in the examination. Now, since you know the reaction is exothermic, so I can say, let's say for example, if I have Na plus gas plus chloride ion gas, right? So I can say this, let's say for example, this becomes Na plus aqueous. Let's keep chloride ion gas. I think this is enthalpy of hydration of sodium ion. Might be the next step you hydrate chloride ion, and this gives you chloride ion aqueous. So it's called as hydration of chloride ion, right? So overall, I can say that this is the overall enthalpy of hydration of both ions. So it's enthalpy of hydration of sodium ion plus hydration of chloride ion. Now the question is, why enthalpy of hydration is exothermic? Let's see a diagram. So can you see that if I actually dissolve a gaseous sodium ion and a gaseous chloride ion, so basically sodium ion and water form ion dipole attractions, whereas chloride ion and H positive forms ion dipole attractions. So technically I think that gaseous ion, when added in water, there is no bond breaking, there is just simply bond formation, and that is ion dipole attractions. So technically ion dipole attractions form, and these ion dipole attractions result in release of energy, making enthalpy of hydration exothermic. So guys, let's see the enthalpy of hydration trend down the group and across the period. So before we learn the trend, I think it's worth sharing that enthalpy of hydration is directly proportional to the charge of cation and the anion, but its inverse radius. I think greater the charge and smaller the radius, more strongly water will be attracted and stronger will be ion dipole attraction. So we can say that enthalpy of hydration is proportional to charge of cation, inverse radius, or enthalpy of hydration proportional to charge of anion and inverse to radius. Let's see down the group first. Okay, so can you see that when you move again down the group, whether it's group 1 or group 2 or maybe group 7, any group, so ionic radius increases, right? Ionic radius increases, but enthalpy of hydration decreases. Why? Because I think the charge remains constant and down the group size of ion increases, so therefore enthalpy of hydration decreases. So I can say that, we can say basically that down the group enthalpy of hydration value decreases. And the reason for the decrease is increase in size of cation. So basically ionic radius increases. So reason is ionic radius increases. So let's see what happens across the period. So basically across the period we have actually metal cations. I think from sodium ion to aluminium we can say the charge increases. Q means charge, right? Charge is increasing and ionic radius decreases. So guys, when the charge increases and ionic radius decreases, it automatically means that enthalpy of hydration increases. Okay, increase means it becomes more exothermic. So I think the alligator signs should look like these. Whereas in non-metal ions, can you see that the charge is decreasing? So the charge decreases. In ionic radius, again decreases. But guys, now I think these two factors are contradicting that whether enthalpy of hydrogen should increase or decrease, because according to charge, hydration enthalpy should decrease, but according to radius, it should increase. So guys, when these two factors become contradictory, you follow charge. So technically, enthalpy of hydration actually decreases because charge decreases. So enthalpy of hydration decreases. Alligator sign should look like this. So now we know that how the enthalpy of hydration varies across the period and down the group. So now let's see enthalpy of solution. Guys, enthalpy of solution, remember it can be exothermic, it can be endothermic. And it's again a physical process, just that we dissolve a compound in water, right? And it's a physical process. The compound should not react with water. So what is enthalpy of solution? So basically, it is the enthalpy change when 1 mole of a substance is dissolved in water to give infinite dilute solution. I mean, the water should be in excess so that all the solute has dissolved. And this substance, remember, it can be ionic compound, or it can be a covalent compound. Like for example, if I dissolve NaCl solid in water, it forms Na plus aqueous plus chloridine aqueous. Now its enthalpy of solution is endothermic, right? But let's say that if I dissolve, let's say sulfuric acid, now it's a covalent compound, in water, so it gives you 2H positive aqueous plus sulfate aqueous. Now I must tell you that its enthalpy of solution is exo. So can you see that enthalpy of solution can be of ionic compounds or it can be of covalent compounds? It can be exo or it can be endo. Now guys, while learning enthalpy of solution, you must know that it can be calculated experimentally as well as theoretically. So let's see the experimental calculation first, and for that you need a couple of operators. You must have a polystyrene cup, an electronic balance, a thermometer. Once you have a hold of these operators, let's start learning the enthalpy of solution of ammonium nitrate. So let's see enthalpy of solution of ammonium nitrate. How do we find it in the laboratory? Here's the question. So it says calculate enthalpy of solution of ammonium nitrate when 10 grams of ammonium nitrate are dissolved in 100-gram water. Okay, by the way, the polystyrene cup has a capacity of 150 ml, right? Or 150 cm cube, or let's say 150 gram, because we treat 1 cm as 1 gram. Initial temperature is 24 and final 17. This shows that reaction is endothermic. So I think on the first hand, you start off calculating how much heat was absorbed, right? The Q is equals to mc delta T. M is mass of water, it's 100. Heat capacity is 4.18 on the first page of data booklet. And I think this delta T is actually 7. If we calculate the value, it is 2926 joules. Now these much joules are actually absorbed. Now let's see how much moles of ammonium nitrate are added. So moles will be equal to 10 is the mass, the MR is 80, so the mole 0.125. So now if we have to calculate enthalpy change, so 0.125 moles absorb 2926 joules, so 1 mole should absorb X. The answer is 23408 joules per mole. But since the SI unit is kilojoules per mole, to divide by 1000, which makes it as 23.4 kilojoules per mole, and the sign is positive because energy is being absorbed. Let's see one more question regarding calcium chloride. When added to water, again, your first catch is to actually find out the heat evolved. Like in this case, are you seeing that the temperature has increased? So Q is equals to mc delta T, mass is water, 15 to 4.18, and the temperature rise is 17.5. The heat released is 3658 joules. Let's see how many moles of CaCl2 are added. So moles equals to 5 divided by its MR, 111. So the moles are 0.045. What's enthalpy change? So 0.045 mole release 3658 joules. So 1 mole should release X. Now X is equals to 81208 joule per mole. But then divide by 1000, which makes it 81.2 kilojoule per mole. But don't forget, the sign is negative. So can you see that enthalpy of solution can be exothermic or endothermic in nature? But guys, in such questions, if we ask you that what improvement can be done, you can place a lid and you can increase the precision of thermometer, and you can, like in this case, can you see 5 grams? It means that the electronic balance used was actually not that precise, as you can see. So if we would have used and electronic balance, which could read up to, let's say, for example, 2 decimals or 3 decimal places. So I think it will be accurate. Okay, so we'll ask such questions in P5 too, or P3 might be. So you can see enthalpy of solution, which can be exothermic or it can be endothermic. Now, guys, we are very well aware of the fact that what is enthalpy of solution? Hydration, lattice. Just a bit of recap. Solution can be exo, it can be endo, and it's of a compound. Hydration is always exo, it's of an ion. Lattice is always exo, but it's always of a compound. Right? And now let's see the Hess law, which connects all these three enthalpies together. Okay? So, if I write this equation, Na plus gas plus chloride ion gas gives you NaCl solid. I think it's enthalpy of lattice energy. If I say Na plus gas plus chloride ion gas, it gives you Na plus aqueous plus chloride ion aqueous. It's enthalpy of hydration, and NaCl solid gives you Na plus aqueous plus chloride ion aqueous. It's enthalpy of solution. Now, if I were asked that I have to connect all these three enthalpies in one Hess law, so can we do that? Yes, we can instantly do that. How? Let's start from any random equation. I mean any random equation. Okay, let's say NaCl solid gives you Na plus aqueous plus chloride ion aqueous. Enthalpy of solution. Now, what if I write gaseous ions here? Now, this is enthalpy of lattice energy, and I think this is enthalpy of hydration. If I make Hess law, and if I, let's say for example, make this as a resultant, so this arrow should go down, this should go up. If this goes down, this becomes lattice dissociation. So can I say enthalpy of solution is equals to enthalpy of hydration minus enthalpy of lattice energy? Is that so? So basically, enthalpy of solution is equals to enthalpy of hydration minus lattice energy. This equation is normally referred to as solubility equation, and using this equation we can actually determine that whether a compound is soluble, or more soluble, or if it's less soluble, or let's say insoluble. Okay, now how do we do that? So it's very simple. Just realize for a moment what's enthalpy of hydration. I think it's formation of aqueous ions. It's formation of aqueous ions. And what is enthalpy of lattice energy? I think it's formation of a solid, ionic compound. It's formation of lattice. So can I say that hydration is actually explaining you that a compound is being dissolved? Lattice is actually explaining you that a compound, a precipitate is being formed. Let's say if I have a compound A, and let's say if I have compound B. Suppose, for example, this is the formula, hydration minus lattice. Let's say the compound A is hydration total, positive and negative, if we add up all together. Let's say its hydration is, let's say, minus 600. Let's say its lattice is minus 400. So the answer is minus 200. Right? So can you see that hydration value is more than lattice enthalpy? It means that formation of ions is more than formation of solid. So overall, ions are being produced. So we can say a compound is soluble. A compound is dissolving in water. So from here we can conclude that when enthalpy of solution is exo, the compound is soluble. So enthalpy of solution, when it's exo, the compound is soluble, or you can say very soluble. But if I have compound B, let's say, enthalpy of solution is equals to hydration minus lattice. Let's say its hydration is minus 500. Let's say lattice is minus 800. So I think that the value is positive 300. So I think solid formation is more than ion formation. The overall a precipitate is being produced. So we can say when enthalpy of solution is endo, the compound is insoluble, or you can say very less soluble. So enthalpy of solution can really explain you whether a compound is being soluble or insoluble. So let's see a question regarding enthalpy of solution, hydrogen and lattice energy of magnesium hydroxide and strontium hydroxide. And let's see some parts related to it. It's quite an interesting question. So in part 1, it's enthalpy of solution is equals to hydration minus lattice energy. Now what is hydration? So magnesium ion is, can you see, its value is minus 1890, right? Hydration. And its hydroxide is 2, so 2 into minus 550. This makes total enthalpy of hydration minus lattice energy is minus 2993. I think the answer is plus 3 kilojoules per mole, right? So the answer is plus 3 kilojoules per mole. Let's use strontium hydroxide, right? So basically, again, enthalpy of solution is equals to hydration minus lattice energy. There is no need to write the formula, right? I'm writing for you so that you should know what I'm doing. So I think that hydration enthalpy for strontium ion is minus 1414 plus 2 into hydroxide is minus 550. So lattice energy is minus 2467. The answer is minus 47 kilojoules per mole. So can you see that enthalpy of solution of strontium hydroxide is exo? I think it's a more soluble compound, and MgOH2 is a less soluble compound. Now he asks you in part 2, use your results in part 1 to suggest whether strontium hydroxide is more or less soluble in water than MgOH2. So I think that strontium hydroxide is more soluble in water. Is more soluble in water because its enthalpy of solution is exothermic. Because its enthalpy of solution is exothermic. He also says that state any assumptions you make. So I hope that the temperature remains constant. So we can say that temperature should be constant. Then he says that suggest whether strontium hydroxide would be more or less soluble in hot water than in cold. Now guys, can you see that strontium hydroxide basically attains equilibrium at its saturation point, where we write this equilibrium. Now this value is exo, as you saw. So he asks you to suggest whether strontium hydroxide will be more or less soluble in hot water. I think that in hot water, system will go backward and it will be less soluble, because if the reaction is exo, it should support low temperatures. So I think strontium hydroxide will be more soluble in cold water and less soluble in hot water. So I think in this question, we'll say that strontium hydroxide is less soluble in hot water because dissociation of strontium hydroxide is exothermic, and you score the marks. Okay, shall we see one more calculation? It's an interesting calculation of enthalpy of solution. I'm showing you two ways to calculate enthalpy of solution, right? So just, I think it's actually wonderful. Let's take an example of NaCl, right? And let's see the two ways to calculate enthalpy of solution, right? Let's see the first method. For example, if we have this data and we have to calculate enthalpy of solution, so I think that you'll be employing the method of enthalpy of solution is equals to enthalpy of hydration minus lattice energy. So I think hydration of sodium ion and chloride ion, I think it'll add up to, let's say, minus 774, and lattice energy is, let's say, minus 778. So I think that the answer is plus 4 kilojoules per mole. This states that NaCl is like you can say less soluble in water at RTP because it's endothermic enthalpy of solution, right? Let's see the second method now. So here we have the data. Now I think if I apply Hess law on it, I know that the enthalpy of solution is NaCl solid giving you Na plus aqueous plus chloride ion aqueous enthalpy of solution. Now its enthalpy of formation is minus 411, its value is minus 240, and this value is minus 167. If I apply Hess law, arrow goes down, arrow goes up. If this goes down, this becomes plus 411. So enthalpy of solution equals to plus 411 minus 240 minus 167. Calculated, it's again plus 4 kilojoules per mole. So can you see that whether I employ the first method or the second method, the answer is same. So guys, we have two ways to find this, and then we ask you these in the examination. So please be careful that we can ask you in any way we want. So it's how we calculate enthalpy of solution. One very interesting thing about enthalpy of solution I want to share is regarding graphs. Right? Let's take graphs of, let's say, for example, lithium chloride and let's say sodium chloride, right? I'm actually making the graph, I mean not the graph, but the energy cycle of enthalpy of solution, hydration and lattice energy, right? You know that enthalpy of hydration of lithium and chloride, if I add it, it's exo. Lattice energy is for sure exo. I tell you, its enthalpy of solution is exo. So if I have to make an energy cycle in energy level diagram like this, so how do we make it, right? Since enthalpy of solution is exothermic, so can I write lithium chloride solid? It gives you lithium ion aqueous plus chloride ion aqueous. This is enthalpy of solution, right? And then gaseous ions at the top always, lithium ion gas plus chloride ion gas, वो तो हमेशा top पे होते हैं. From gaseous ion to solid is actually enthalpy of lattice energy, but from gaseous ion to aqueous is enthalpy of hydration. So can you see that enthalpy of hydration is actually more than lattice energy, making enthalpy of solution exothermic. At the same time, we can also draw this cycle for NaCl. Enthalpy of hydration of both ions add up, it's exo. Lattice, of course, is exo. I tell you, its enthalpy of solution is endo, by the way, we calculate as well. So we always draw enthalpy of solution first, the easiest way. But now guys, NaCl solid, the arrow should go up because it's endothermic. This is Na plus aqueous plus chloride ion aqueous. Now this is enthalpy of solution. It's endo. Now gaseous ions are always at the top. Na plus gas plus chloride ion gas. Now from gaseous ion to aqueous is enthalpy of hydration, and from gaseous ion to solid, now this is enthalpy of lattice energy. Now can you see that hydration enthalpy is less exo than lattice enthalpy, making solution endothermic? I think that with these two cycles, they can be for any solid whose solution is exo or whose solution is endo, right? So we can ask you these these energy cycles too, of course, in the examination. So you can practice May, June 2012, right? It's component 42 and it's question 1. It's a good question. You can always give it a practice and find out how we ask you things about enthalpy of solution, hydration, and lattice energy, right? Just remember that whenever you have to find out enthalpy of solution in the laboratory experimentally, right? For example, so you must know mass of water, you must know mass of substance whose enthalpy of solution you're finding out. You must know the initial temperature. You must know final temperature. I think these three are these four are the measurements which are actually required every time if you have to calculate enthalpy of solution. Now, guys, once you've learned enthalpy of solution, hydration, lattice energy, it has a very good application in group 2, right? Where we explain solubility of group 2 sulfates and hydroxides down the group. So let's see solubility of sulfates and group 2 down the group. Let's see group 2 sulfates first. So here are group 2 sulfates. So remember that barium sulfate is aqueous. This is aqueous. Now solid, 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 solid. So basically, can you see that down the group, solubility of sulfates is decreasing. Now, why it is decreasing? So let's see the concept. So basically, I think the size of cation is increasing. The charges of cation, anion, and the size of anion is constant. Only size of cation is different. So, I mean, down the group, we can see that size of cation increases, which means enthalpy of lattice energy decreases, which also means enthalpy of hydration will decrease altogether because size of cation is actually decreasing. Now, both enthalpy of lattice and hydration are decreasing. But how they actually explain enthalpy of solution? So let's see some hypothetical values and then I'll explain you the concept. Uh, let's say enthalpy of solution is equals to hydration minus lattice. Now I'm taking hypothetical values. Now barium sulfate is aqueous, so it means that its enthalpy of solution should be exo. Let's be random. Let's say its hydration is, total is minus, let's say 100. Total barium sulfate, beryllium and sulfate मिला के. And let's say its lattice is minus 80. So the answer is minus 20, which means that enthalpy of solution is exo, the compound is soluble. Now when you move down the group, lattice energy decreases, hydration energy decreases. But can you see that down the group, the compound is becoming solid, which means hydration energy actually decreases more in value. Let's say the value comes up to be minus 40. Lattice is also decreasing, but not that much. Let's say it's minus, let's say 50, which makes it plus 10. Have you seen that enthalpy of solution has become endothermic? So how do you write in the examination? So you say that down the group, both enthalpy of hydration and lattice decrease because size of cation increases, but enthalpy of hydration decreases more than lattice energy, making enthalpy of solution endothermic and compound insoluble. Thus, solubility of sulfates decreases down the group. Now, this carries normally 4 marks. Having mentioned that both hydration and lattice are decreasing, 1 mark, but hydration decreases more than lattice, 2nd mark, making solution endothermic, 3rd mark, and then lastly, solubility of sulfates decreases, it carries 4 marks. Now, solubility of sulfates decreases, but what about solubility of hydroxides? Here is group 2 hydroxides. Can you see down the group the compounds are becoming aqueous? I can say solubility is increasing down the group, right? Again, the concept remains same because size of cation is increasing, right? So down the group, size of cation is increasing, right? Both lattice energy and hydration should decrease, right? So let's take the equation and see the hypothetical values, hydration, and then we'll explain, of course, lattice energy. Let's say the total hydration of beryllium hydroxide, let's say total is let's say minus 130. Let's say its lattice is minus 170. Can you see it's solid actually? That's why I'm trying to make enthalpy of solution endothermic. I think it's plus 40. Down this group, both decrease, but I must tell you now the lattice decreases more, which means that let's say hydration enthalpy now is minus 90, but let's say lattice is minus 60, the answer is minus 30. So can you see that in this case both have decreased, but lattice has decreased more, making solution exothermic and the compound soluble. But how do you write in the examination? Now this explanation carries 4 marks again. Both hydration and lattice decreases, that's a fact. But now lattice decreases more than hydration, 2nd mark, making solution exothermic, 3rd mark, and then stating solubility increases, and 4th mark. Is that so? So we can draw a conclusion, right, that in case of sulfates, solubility decreases, in case of hydroxides, solubility increases. Like very famously, we use barium compounds. So I think that it should be in your brains that barium sulfate is an insoluble salt, but barium hydroxide is a soluble base, right? Interesting. Guys, it's an interesting question. Some people get stuck in it. Let's see how to solve it. So this is X, right? So you know that if I atomize Ca and form Ca gas, right? So this value is plus 178. Then if I ionize it, Ca plus 1, Ca plus 2, if I make it Ca plus 2, I think it's sum of both its energies. So basically it's 590 plus 1150, right? And Ca plus 2 aqueous is hydration. So its hydration is minus 1576, as you can see from here. Now, since I have made calcium ion over here, now this can be balanced. Now let's atomize this. It becomes 2H gas. It's actually bond energy of HH found in booklet 436. Ionize it. It becomes 2H plus 1 gas. It's 2 into 4 as energy, that is 1310. And then you hydrate it. 2H plus aqueous. It's 2 into minus 1090. Now can you see that this is balanced with this now? Now this makes one complete Hess law. So basically, can I say that this plus this is equal to this? So I can say 178 plus 590 plus 1150 minus 1576 is equals to x plus 436 plus 2 into 1310 plus 2 into minus 1090. If you calculate it, the answer comes up to be minus 534 kilojoules per mole. Isn't it nice and easy and interesting? Basically, it is just a matter that spend 1 or 2 minutes, just see which data is given, and just realize how to balance the Hess law. And I think you can go very well in it. So, guys, I hope you liked enthalpy of solution, hydration, and lattice energy now all together. We did some amazing questions too. We had some nice interaction. I hope that you enjoyed it. One last thing. Now, since we discussed much about water, that is hydration, solution, stuff like that, just a tip from a chemist. Uh, if you want to really improve your immune system, if you want to be active, right, then start drinking ginger and lemon tea, right? You know what? Both ginger and lemon have healing properties. I think you should buy organic. Like if you ask me, I don't like spending on vegetables having, all the chemicals sprayed in them. So buy organic food. This lemon has vitamin C and it can really support your immune system. Uh, and this ginger, it's actually antispasmodic. If anyone has muscle spasms, you can actually, make a drink out of ginger and you can have it. It has a good, and it's a good heating food as well. I mean, if it's too cold outside, you can have a ginger tea and it can actually soothe you down in such cold weather. So basically, all you need is ginger, lemon, water. So all you need to do is have a glass of water in a pan, right? Add 1 or 2 ginger roots, of course, peeled off. Let it boil. Then you have to put that ginger water, stain it, and put it in a cup. Add some lemon, add some honey, enjoy the flavor. Sip it, enjoy it. And I hope that your immune system will get better. You will reduce your fat, you can reduce your belly, and then, of course, you will enjoy chemistry, right? And the catchy thing is, you can have it hot or you may have it cold. But I must tell you, one sip and you'll be in heavens, right? So, guys, this was Chemistry by Muhammad Ali, this was Energetics, and this was a tip. Happy learning.